Thank you, Greg. Okay, so we know that environment drives galaxy evolution. We also know that stellar mass drives galaxy evolution. And at low redshift, redshift 0, the fraction of quenched galaxies is correlated both with stellar mass, but also with environment. So there are two ways to kill a galaxy. Now, at low redshift, it's been shown that the effects of stellar mass and environment are completely separable. And these two distinct processes of mass quenching and environment quenching have been introduced. And what my talk is all about is trying to extend this to higher redshift and also to try to actually understand what the physical processes are that do the quenching. One of the problems with current generation field galaxy surveys is they're not large enough to really sample the densest of environments. So if you want to understand the effects of environment at high redshift, you can't do it very well with field galaxy surveys. The only way you can do it is if you actually target rich clusters directly. Your first problem is finding rich clusters. It's actually technically quite challenging. You need a wide survey because the number density of rich clusters drops off pretty rapidly above redshift 1. But you also need a deep survey. No matter what technique you prefer for cluster detection, you've got to detect your photons one way or another, so you need a wide survey. So the challenge is to find a deep survey and a wide survey. So a few years ago now, we started SPARCS. We use infrared detection to find our clusters, and we combine Z-band optical imaging with infrared imaging from Spitzer. We have a 50 square degree survey, and we found about 200 new cluster candidates above redshift 1. So that's great. We've got now some samples of clusters to follow up and study. And you want samples. You don't just want one cluster because one cluster might be atypical in some way or another. So what do we learn about clusters at redshift 1? We took 10 of the most massive halos from our survey. There they are in all their glory. And we decided to hammer them. We want spectroscopy. You need spectroscopy for all sorts of reasons. So we started this project. It's a pretty large 25-night multi-semester project with the GMOS instruments on Gemini. We've got 10 clusters that are between redshift 0.87 and redshift 1.34. And after a lot of work, we ended up with about 500 members total amongst the 10 clusters. This is a lot for redshift 1. So this is our sample. And we'll start off with stellar mass functions. We'll talk about the satellites first. So what you see here on the left in black is the cluster stellar mass function combining the data from those 10 clusters of redshift 1. So that's on the left, and then on the right there's the field galaxy stellar mass function, and the field galaxy data is from UltraVista. And we've also broken down our stellar mass functions by quiescent in red and star forming in blue. So the first thing you can see very clearly, you can see it on the bottom here, is that there is a higher fraction of quiescent galaxies in clusters versus the field. I'm not really telling you anything new here, but I'm reminding you that this means there's significant environmental quenching going on at redshift 1.
How do you tell the difference between the two? What's the definition?
Whether you see O2 or not. Okay. So,
not an UltraVista.
UVJ, I think.
UVJ, yes, thank you. For this paper, it's UVJ.
For both?
Yes.
Okay.
All right, so here what we've done is we've compared the shape of the stellar mass function. So cluster on the left, total cluster, I showed you that in the last plot. Total cluster stellar mass function is in black, field is in pink, and we've scaled them. We've just scaled the field to m star for the cluster. And now it starts to get interesting, because we also broke it down by star-forming galaxies and by quiescent galaxies. And you can see that the shape of the stellar mass function for both star-forming and quiescent galaxies is similar in the cluster and field environments. So what I'm saying here is, if different processes are responsible for quenching star-forming galaxies in the different environments, they have to work in such a way that the shapes of the star-forming and the quiescent stellar mass functions are similar. So I'm sort of throwing down the gauntlet here. I'm saying, look, we have good measures of stellar mass functions at redshift 1, and now the challenge is to the models to reproduce what we're measuring. And just from simple argument, simple model, we can show that about 45% of the star-forming galaxies, which normally would be forming stars in the field, are quenched by the cluster. So that's what the cluster does. It quenches 45%.
What is the mass range for clusters?
Say again?
The mass range? How massive are your clusters?
Can't understand. What did you say?
How massive are your
The
clusters?
halo
Oh. Oh, it's just in velocity dispersion there. A few times 10 to the 14. But they'll grow into coma by the present day. All right, so we've done stellar mass functions. So let's look a little bit more detail. Environmental versus stellar mass quenching. How fast can each process kill a galaxy? So what you see here is the star-forming fraction at a fixed stellar mass, and there's a slope. This is for 3 stellar mass bins. There's a slope, so there's a correlation between the star-forming fraction and environment. We're using radius here as our proxy for environment. There's also a correlation, which I haven't shown here, between the star-forming fraction and the stellar mass. And this is exactly the same as found at redshift 0. Now, plot specific star formation rates of star-forming galaxies. Now, you don't see a correlation. These plots are flat. So, the specific star formation rate of star-forming galaxies, it correlates with the stellar mass, but it doesn't correlate with the environment. This, again, is what is found at redshift 0. You scratch your head over this for a minute or two, and then you gradually begin to realize that these results can be reconciled if environmental quenching is a much faster process than stellar mass quenching.
Can you explain that?
Yes, because you're moving your galaxies out of the star-forming fraction so fast that you don't see them in this plot on the right. So the analogy here is that environment is like an on-off switch. We've got the light switch analogy. Environment is like an on-off switch. It quickly moves galaxies between star-forming and quiescent. Stellar mass is more like a dimmer switch. It smoothly regulates star formation. As your stellar mass goes up, your star formation rate goes down.
It goes up too. If you're on a star forming main sequence, the star formation rate goes up. The specific star formation rate's down, but the star formation rate for big galaxies is bigger than
Okay.
small ones.
So I want to talk about post-starburst galaxies. You find a surprisingly large number of post-starburst galaxies in clusters. And this is another clue. Maybe we're onto something. Maybe something is quenching these galaxies, doing it pretty fast in clusters. So I'm going to show you a phase space analysis that we've done. This is a pretty powerful tool for figuring out what the murder weapon is. Okay, I've got Eric smiling again. Okay, good. He's not causing trouble for a couple of minutes.
I did enjoy clearly.
So if It's Cluedo, Eric.
I know.
But for our American audiences, it is Clue. So if you'll just follow Professor Plum and myself into the conservatory, we'll see what we can do with this. So this is a plot of velocity versus radius for all 10 clusters in our sample. And we've broken it down again by type. What you see on this plot in green is where the post-starburst galaxies lie. They're found at, you can see, at small radii on the left on the x-axis. But they've got pretty high velocities. They tend to avoid this central region. So small radii, high velocities. Now we're going to play a little game. We're going to have a toy model. We're going to say, we're going to give ourselves three options. We're going to assume quenching begins at 3 different radii. And we're going to assume it can either be fast or slow. And then we're going to compare our results, our observations, to simulations. And we're going to see if we can learn anything. So we'll give ourselves 3 options. It's like the Goldilocks game here. You can assume quenching begins at 1 virial radii. You can assume quenching begins at half of R200, so where the dense ICM begins. Or you can assume quenching begins at 0.25 R200. You have to wait till you get to the cluster core to be quenched. Okay, so then we're going to compare against our various options and see if we can learn anything. And quenching can either be fast or slow. So here are the results from simulations. Quenching at virial radius, half virial radius, and a quarter virial radius. That's when the quenching begins. And then, does it happen slowly or does it happen faster, left and right? It's kind of hard to tell which is the winner from this plot, but when you look at this more carefully, the best match is this one, the data. Quenching begins at half of R200, and it's pretty fast. Now, it's a time model. Don't pin me down to these exact numbers, but it's kind of interesting to see where this can take us. So this scenario is qualitatively similar to the delayed then rapid quenching model, which has been proposed at redshift 0, but the quenching time at redshift 1, that's roughly similar to that at redshift 0, but the delay time may be a factor of 2 to 4 faster. So the delay time is cut, and then the quenching time, as far as we can tell, is about the same. So, what's the murder weapon? What's the process that causes environmental quenching? So R-derived quenching location is half of R200. That's here. So our conclusion is that the quenching location and time scale are consistent with either hot halo gas stripping, strangulation, or cold gas stripping, ram pressure stripping. We can't really tell the difference, but we pin it down to those two. It's pretty good. More data will do better. And also a redshift evolution of the quenching time could perhaps break the degeneracy. So this is just a start, but I think it's pretty promising. And obviously, a lot more to be done. Okay, now I'm going to switch gears. We've done the satellites. Now we're going to do the centrals, brightest cluster galaxies. They're nice. They're easy to identify observationally, for the most part, and in simulation. So they're an attractive target for testing our understanding of the processes that drive evolution in the most massive galaxies of the universe. So to cut a long story short, we find that brightest cluster galaxies doubled in stellar mass since redshift 1. This is in good agreement with simulations. It was a bit controversial because other observational studies had claimed that there was no evolution in the stellar mass of BCGs out to redshift 1. But we don't agree with that. Previous analysis, there were some issues with the previous analysis, and particularly didn't properly take account of the mass of the cluster, and as you can see here, the BCG stellar mass scales with the cluster mass. So, okay, so how does the BCG grow in stellar mass? Again, simple model, 3 options. Equal mass mergers in blue, minor mergers in green, expansion in red. So we rule out, since we're growing in stellar mass, we have to move to the right on the x-axis. Can't be expansion, has to be equal mass mergers or minor mergers. If you look at the sample, you notice that several of the BCJs have actually got bright nearby companions. And you can work out a time scale for the merging. It's not too difficult. It depends on the projected separation, the relative velocity, the mass, and the redshift. It's about this, 600 million years. This plot shows the number of major mergers you would expect as a function of the fractional increase in the BCG mass and the merging timescale. So we can have red is 1 gig a year, green is 0.6, blue is 0.2. So we have a sample of, in this case, 14. We expect 3. And how many do we observe? We observe 3. Now this is too good to be true, okay? That was almost too good to be true. But our conclusion from this is that most stellar mass growth by BCG since redshift 1 is as a result of major mergers.
How are you defining major versus minor?
Based on the stellar mass.
Well, like 1 to 1 or 2 to 1? Or
Yeah.
Which one?
I have to look it up. I can't remember off the top of my head. There's a cutoff, I just don't remember what it is from the paper. Okay, so anyway, before I move on. So obviously there's still some room for minor mergers, but our conclusion is that most of the growth in the centrals since redshift 1 is in major mergers. All right, so my last minute or two, I'm going to talk about where we're going from here. We're pushing out in redshift. We have managed to confirm some clusters, in this case here 4 above redshift 1.5. And as far as the observer's world is concerned, multi-object near IR spectroscopy is going to revolutionize the studies of galaxy clusters at these redshifts. For these 4, we also have HST data being taken in cycle 21. And now we can get at things in the redshift desert because of this new generation of multi-object near IR spectrographs.
Isn't there supposed to be no redshift desert if you use live alpha and a very good spectrograph? I'm wondering why the near IR is so important.
Not for non-star formers.
Doing what? Okay, so you're using rest frame optical absorption lines? It's pretty tough.
That's what
Thank
you
you.
were saying. Thanks.
Thanks, it is tough. Pay me more. Okay, so we know that galaxies and clusters do not lie on the fundamental metallicity relation. I'm throwing speculative stuff up here at the end. For a given stellar mass, galaxies in clusters have higher metallicities. So environment must be a 4th fundamental parameter. We're looking for fundamental relations. This is some data from Mossfire on Keck. This is emission line galaxies. Here you see H alpha. Here you see weak N2. And we can use the H alpha and the N2 to measure both star formation rates and metallicity. So now we can get a handle on this relation at redshift 2 or so. There's an interesting and quite controversial claim. One paper has come out already claiming that there is a mass-dependent environmental trend at redshift 2. It's a bit strange because it says the most massive galaxies in the cluster and in the field don't show any difference in metallicity, but at lower stellar mass, there is a difference. So that's a little bit controversial. Now we have our own data set, and we'll have more to say on that in the future. But could be interesting. Anyhow, I'm not going to read everything on the conclusion slide, because I think I've said it all, but the point I would like to make is that thanks to these types of instrument improvements, the next few years will allow us both to push out in redshift, so we'll be able to address environmental questions at even higher redshift, but will also allow us to push down in stellar mass. Greg and I are involved in a proposal that just got accepted to Gemini. It's in this new large and long category, and so it's a 3-year survey, and we'll be able to push down in stellar mass in the G-class clusters and some other clusters that clusters and groups that we've added in there. So that's pretty exciting for us, and that's going to be keeping us busy. Thank you.
Okay. Evan? So your constraining of the quenching timescale inside the cluster sort of really hinges on what you call quench. So I'm wondering, if you started off on the main sequence at that redshift and then dropped off the main sequence, how much room would you have until you would call it quenched?
Well, there's the other issue that there may be things that start quenching at, there may be, you may have things that are quenched in the outskirts of clusters, and then they fall into the cluster quenched, and they're not in this sample either. So, rather than get into we're arguing about this timescale versus this timescale, I'm throwing out that this is the big picture, and yes, now we have to look at the details of it.
A quick comment and a quick question. The result that the delay time that you found was about a factor 2 to 4 shorter than what we inferred at redshift 0 with the group catalog and Wetzel et al. It's perfectly consistent with what you would expect, given that the dynamical time scales as 1
Yes.
possessor 3 2.
Yes.
So it's basically perfectly consistent.
Yes. Mm-hmm.
I just wanted to ask you about your statement that the environment quenching was fast, and I agree with that. The actual quenching was fast. But that the mass quenching, aka the quenching of central galaxies, is slow. I don't agree.
No, I didn't say anything about the quenching of central galaxies.
You said mass quenching is slow. That's what you said.
She
No.
said mass,
Yes, you said that.
mass evolution or whatever. She didn't say the word quenching, because she was talking about the evolution of specific stuff.
You had environment quenching and mass quenching, and once was a light switch and then it was a dimmer.
It was a dimmer.
Right. I don't see why you would think it's a dimmer, because I don't agree with that, because that would mean that if I look at central galaxies in different environments, at some point I should see a certain range where there's a buildup of green valley galaxies. So I think even for those central galaxies, or that mass quenching is fast, it just doesn't happen always at one particular mass scale or something, but its actual quenching must always also be fast. That's sort of what we claim, at least. That's all quenching is fast. The actual transition from blue cloud to red sequence always goes on the time scale of 0.5, 0.8 gigahertz.
Okay. Let me come back to that. We see the correlation on the stellar mass function that we don't see for the environmental function. So I'll talk to you about this, I said, because it's going to take too long.
Tim? So, coming back to the point about these different quenching mechanisms,
Yes.
and the timescales and the clusters, quenching mechanisms you highlighted are very good at stopping new gas coming in, but they don't remove the gas that's self-forming right now, and that will stay around for 1 to 2 gig years. So how does that play into your picture?
The stripping takes that gas
So
out.
you have to do very, very much the centre to remove the cold molecular gas, because it's very much bound to the galaxy in the very centre. Okay, there is no observation of stripping of molecular gas in
I'm
the
going to bring up this.
The outskirts
It's
is
got lower
straight.
definition.
The outskirts
There is
is
just
not
as
the
much
star
many
forming
galaxies
regions.
in Virgo to take the molecular gases in the field.
Yes, molecular gases.
Yeah, you can strip
Yeah.
molecular gas.
See molecular gas strip, and you see star formation there.
It's not the dominant crust.
You see the star formation regions
It's not
outside
gas
the galaxy.
in the centre. You get H1 strip, which may form molecular, but the gas in the centre stays around, even in the very centre of the
But
gas.
you're making the assumption that the only molecular gas is in the center.
Sure, if there's gas on the outside, that's fine, but you're going to
Yeah,
have
it's not-
gas
it's
in the
not-
centre that's tightly
It's not
bound.
the most gas that's responsible for star formation. Most of the gas that's forming stars is not stripped. Except in a few exceptional
I do
cases,
not-
that's why people write papers about it.
You really get
I do not believe
I think it sounds like an excellent discussion for coffee.
It's good, we've started a discussion, that's good, right?
So let's thank Gillian again.